Hello everyone, welcome to the new training campaign which will be about MIMO and Massive MIMO. Actually in this campaign we will explore MIMO details and even will dive deep into the Massive MIMO even for 4G and 5G because I believe it's similar. We'll explain about that will help you understand the details of wireless communication in general, optimization. So actually as you can see here, all these points which we are going to cover in this training. The training will be I will try to cover the training maybe in 5 or 6 sessions. It might go more than this, but I will try to keep it as short as much as I can. So actually, as you can see here, the first session we are going to cover it will be, which is today's video, or it will be about the MIMO introduction in general. And this will be covering a very important details which you will really need to understand before deep diving into the details of passive MIMO, because and all these points you will really it will really make it very easy for you to understand all the remaining training. So this session is very important, even it's having many theoretical information, but it's really important. You need to give a full focus for this session. Then after that we'll go through before jumping to the second session, which is about introduction of massive MIMO and details about massive MIMO. We'll just give a short session about some to recall or recap some knowledge about the 4G in general. For example, what is the transmission modes, how it was being mapped for the reference signal and antenna ports, because also this will make it easy for you to understand all the remaining points. So we'll cover like what's the massive MIMO in general, then we'll go through the deep dive of the beamforming in massive MIMO, especially in NR, and the beam management, which is covering very important points about the initial acquisition, like mobility, beam failure, recovery, and all these kind of points. Then we'll go through this topic, which is about very important concepts about the code words, layer mapping, and port mapping, and so on, and even the antenna and port mapping. And also that these points will probably be covered within all the other sessions. So now let's move to our first topic, which is introduction about the MIMO and all these kind of ones. So this is actually the first part we're going to cover today. It's like just giving you a high-level introduction about the differences between the traditional MIMO and massive MIMO, which is mainly it's in the type of the antenna being used in both of them. For example, in the traditional MIMO, as seen in the figure in the left here, it was using something called passive antenna. And the main idea of the passive antenna, as you can see here, that we have the amplifier or the RRU, which is responsible to the transmitting the power and these kind of things. It was being connected to the antenna, and this antenna is called passive because the RRU is separated from the antenna itself. So was actually the main first point, which is the main difference between both of them. Secondly, that in traditional MIMO or in the passive antenna, the maximum supported was up to 8 transmission and 8 receiver, which is less than or equal to 8 transmission or 8 receiver. And the remaining is like kind of similar. We have a fiber connection, which is ECPRI or ECPRI fiber cable. Then we have here the coaxial cable, which is connected from the RRU to the antenna, and this will be replaced later on. So before explaining about the active antenna, I will just want to you like how this kind of antenna looks in the real life. So if you look into this figure, for example, here is the antenna. This is where it's being shown here. This is the backside. And in the bottom down here, there is the RRU being connected to the antenna itself. And in bottom down here, you have, as you can see, some cables being connected through some ports and so on. So this is the bottom down of the antenna. So usually in the traditional MIMO, the passive MIMO in general, passive antenna in general, this is being used for different technology. Maybe it can connect 3G, 2G, and even 4G. And I think in the future also some of it can support even the FDD-NR. For example, here can be some ports using for 1800, 2100, 800, 700, 900, and so on. And you should call it, for example, GUL, which is stand for just MTS and 4G. For the active antenna, actually, the main difference is again where we highlighted. The first part, it's about now it's called active antenna instead of passive antenna. As you can see here in the massive antenna or active antenna, this is like they have integrated the active antenna in general integrates the antenna and the RF unit or the RRU, and this is into one unit which is called AU or AS, which is called active antenna. This is the first differences, and this is kind of integrating the RRU or the RRU or RRH into the antenna itself. This is can reduce some feeder loss. As you can see here in the massive MIMO antenna offers or active antenna offers first of all decreasing the feeder loss, which is this particular part on the left here. So you don't have that, no, because now you are connecting directly to the BDU through the ACBRI or through the fiber in general. So this is the first point which is being gained through adding the active antenna. Usually the loss is around 0.5 dB. The second part, it's about the massive number of antennas. That's why it's called massive MIMO, because it supports massive number of antennas. It usually starting from 16 transmission, 16 receiver, up to 64 transmission receiver. Even there is even much more 128, but the majority being used now even 32 or 64 for the massive MIMO. And this is actually active antennas, not only for 5G, it's also used for the 4G, especially for the TDD mid-band, which is starting from 2.6 as well. So it's not only 5G, it can also be used for the 4G. The next here, it's about the integrating. As you can see here, this is the main differences, decreasing the field loss. And this one introducing a very high number of antenna elements into the antenna, which is actually, that's why it's reflecting in the number of transmissions. So let me show you. First of all, this is how the antenna looks like. There is no any more RRU, just as we shown here. This is how it will looks like. And this is how it looks like of the antenna, how it looks like. You can see there is a very small unit inside here. Many of them. This is like 64T, 64R. This is a very small unit. It's called antenna element. And this is actually, I will go through this in much detail in the next slide. But this is a basic building block or of the antenna array or array. And this is single unit, which is a single radiating unit, such as dipole. This is I will go through these details, but just remember this figure because we'll go through all of this in details in next slide. So this is how it looks from inside. Now let's jump into the details about other information, especially about the antenna specification, which is also very, very important to understand, especially when you read the antenna data sheet and so on. So to really understand what is from where the gain coming from the massive MIMO, especially when you read the antenna specification. Okay, this part actually it's about, as you can see, this is the antenna solution and this is the antenna specification in general. Actually, antenna specification, this some of them or majority of them is being included even in active or the passive active antenna or the passive antenna. I tried to summarize it here as much as I could or as I can. As you can see, first of all, the most important one, which is about the antenna gain. Actually, the antenna gain is one of the most important indices of an antenna in general. Let me zoom here just to give you some clear figure about it. For example, if I zoom here to this main loop, as you can see the right side here, actually the antenna gain in general, it indicates the antenna capability of centralizing the energy in the center direction. For example, you can see here this particular beam here is being the energy being centralized here. So this is the main loop. So this is actually the maximum gain. Usually the gain is in dBi. I refer to isotropic antenna. So this is referring to the maximum gain of the antenna at this particular, for example, direction. This is the first point about the antenna gain. This is very, very important whenever you read the antenna specification. Before continuing into the other all the other stuff here, I just need to use just one simple stuff about the antenna specification. As you can see, this is just some sheets quoted from the internet. For example, the first one, the top left, top right here, this is related to the antenna specification. We just mentioned some of whatever we have here. For example, the polarization mode, we'll go through it in details. And here, for example, I mentioned that the gain is 25 dBi. And there is something about the horizontal sweeping range of beams and even the vertical sweeping beam range of beams. I will explain this in shortly about these two parts. And here, for example, this was another antenna, was for the active antenna. As you can see, it's having a lot of details about the supported frequency. This is also should be found in active antenna as well, the gain, and also return loss. And you have something called polarization, again, we mentioned here, and the electrical down tilt in general, the ranges or adjustable. For example, here he mentioned from 0 to 10 degree and something about the front back ratio and other mentioned points, which we'll cover most of them now. Now let's continue with the remaining stuff, which is really very interesting. One of the other specifications is called front back ratio. Actually, front back ratio, it's like very simple. As you can see here, there is in the back side, which is called usually the back loop. This is like the antenna radiates in the opposite direction of the main loop. And this is usually it's unwanted signal, which can cause interference for any, like for example, if you have sides in the background here and transmitting in the same direction, this is can kind of cause interference. So the less you have from that, the better the performance and the better the beam efficiency. So actually, one of the things which is introduced in the active antenna of massive MIMO in general, that it's trying to reduce this backside as much as it could. Even for the side loop as well, this is one of the definition. As you can see, side loop, this is like, for example, the side loop of the antenna here, and the left and right here. And also, as you can see here, for example, this is the main loop, and this is the side loop as well. And actually, the stronger the side loop, this is also can cause interference, and this is called, again, unwanted signal. So the less the side loop and front back ratio or back loop, the better the performance of the antenna. And this is usually actually called the beam efficiency. So now let's move to the remaining points, which is very, very important as well. Before going to the polarization, and the frequency range is very simple, just like one of the specification, it will just directly mention that this, for example, antenna supporting this particular range of frequencies, for example, it can tell you supports from 3,400 gigahertz, 3.4 gigahertz, 3,004 gigahertz, up to 3,008 gigahertz or 2.6 or milliwave band and so on. So this is just telling you exactly about the supported range of frequencies. One of the most important factors as well is the number of the supported transmission and receiver of the antenna. For example, 44R as an example for the traditional MIMO of the active antenna, and even for the passive antenna up to 64R. And how this come from? It came from something called antenna elements. That usually in antenna elements, I'll go through it in details. I already gave some explanation about this is the basic unit or building unit block of the antenna array in general. I will explain this kind of terminology or numerology about what it means by antenna elements, array, and subarray in the next slides. But antenna elements in general, this is the more the antenna elements, the higher the gain of the antenna. And even this antenna elements itself, it's control a lot of points. For example, we mentioned before about the controlling the tilt ranges. The higher the antenna elements, the more the antenna elements, the more ranges where you can control from the tilt. For example, instead going to 10 degree, you can go up to 15 degree and so on. Even the beam efficiency will improve. The beam efficiency actually, it's just meaning as mentioned here. This is telling you what is the portion of the total power radiated by antenna contained in the main loop. For example, the higher the main loop, so the back and front back ratio might decrease, and even the higher the beam efficiency means you have a better antenna, and this can suppress the noise or the interference from the back and side loop as well. So this is also one of the things. If you have higher antenna elements, you have a better beam efficiency, and even the antenna directivity will increase. And this is kind of form of beamforming as well, or antenna array gain, and so on. And even the MIMO gain in general will be increasing and go through all these kind of details. And one very important point as well, you have something called horizontal sweeping range of beams and vertical sweeping range of beams. You can control, for example, if you zoom in here, you can control, for example, you can have some control over the ranges whenever you tweak or change or tune the horizontal beam and vertical beam. Usually in the massive MIMO, you can have some ranges, for example, going in the horizontal from left to right by this kind of ratio or angle, and also for vertical, it's same up and down how much it can move. And for each angle of each scenario, like you have usually different coverage scenario or different angles for each one of those, what will be the gain expected for each of the angle you are going to tune. This is usually this is actually how it will looks like. You will have different ranges of tuning. For example, here is mentioned at horizontal 3 dB beam width. This is the maximum gain of 3 dB. You will have at 110, and equivalent for 110 degree for the horizontal. You will have around centigrade for the vertical. And you can start tuning this based on your scenario. For example, if you would like to have a higher gain to make higher vertical angles, so you can increase them to 12. So you can have, for example, 3 dB at 12 angles. So this is just explaining you what is the range of support of the antenna. And even you can see here the tilt adjustment, as we mentioned before, this is controlled by the antenna elements in general, and also you have a different ranges for each antenna. The last one, which is I would like to explain as well, it's about the polarization. Actually, polarization is really antenna polarization. This is really very, very important. We have different types as mentioned here, but let's quickly recap something here. If you remember, in general, in the polarization means referred to how the radio signal in general being transmitted from one antenna to another antenna. And during the propagation, you can have a different reflection, especially in the mobile communication. For example, you can have a free bar space. For example, there is no reflection or no obstructions. The signal can directly move from the transmitter to the receiver, or we can suffer from some reflection. For example, here in the ground reflection, as mentioned here, as shown here, and even some directed passes blocked by obstruction called knife edge, and this can make a diffraction or diffraction loss. Even you can sometimes have a penetration loss or multi-path propagation, and this is also majority of this can cause this kind of something called fading in general, and this is all being addressed in general by the MIMO or the MIMO and other stuff we'll explain in the next slide, and also the polarization antenna polarization type play a role in improving this kind of things, which we'll explain shortly about how it can work. So what it means by antenna polarization, let me zoom here just to give you some figure about it. Antenna polarization in general, it refers to the orientation of the electromagnetic waves, like how the electromagnetic waves is being transmitted or received, emitted or received by the antenna itself. And like you can, as you can see here, for example, you have vertical polarization, which is moving, as you can see here, moving up and down. Even you have the horizontal polarization, which is moving from side to side. As you can see, this side, for example, left is right here, and this is up and down. And you have something called plus minus 45 polarization, usually they call it slant polarization. And this is how it usually looks like in the antenna. So what 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 means by this? This is again, it's just how the signal being emitted, and you can think it like a rope. For example, if you have a rope in your hand, and the way you move this kind of rope, yeah, you're moving your hand, for example, up and down or side by side or in circles, and this is you will determine how the rope is in general is being traveled or being moved. This is kind of similar if you're going to make some simple analogy. The main idea here that we have different types. We have the linear, which is consisting of these three types, which is vertical, horizontal, or slant. The most common one is used as currently, even in the passive active antenna, called slant with slant actually, which is having this kind of the slant dual polarization, which is plus minus 45 degree. And the main advantage the slant and why it's being used, that the signal actually, or the transmit or receive signal can be received even in both vertical or horizontal direction. And this is good in general for MIMO, and it can help also. The signals can arrive from different directions with varying polarization. For example, it can arrive in horizontal, it can arrive in vertical. So having this kind of dual polarization allows the antenna to capture these kind of diverse signals component effectively. Also, this is it can improve something called it allows for polarization diversity. It will improve the diversity, which we'll go through details in the next slide as well. How do that? For example, different polarization journal, as you can see, plus 45 and minus 45, plus 45 and minus 45, as you can see it here in general. This is different polarization may experience the fading in general, independent fading in general, and can improving the signal reliability through the diversity again. So in summary, this kind of dual polarization, which is called slant polarization, it can improve the diversity. So that's why this is the most common use now, even in passive or active antenna. And there is another type called circular, which can be clockwise or counterclockwise. And usually the circular is being used by the device, which is a mobile device. But for the antenna itself, the unit B or unit B antenna, it will be using this kind of dual slant. Now let's move for a very, very important part, which is called antenna terminology, which will explain in details more about the antenna elements and the subarray and the antenna array in general. And this is really, really very important because it will pave your understanding about the massive MIMO or reactive antenna in general. It will let you explain from where the gain is coming and why massive antenna is much or massive MIMO is much powerful compared to the active antenna. So let's move forward. Okay, here there is a very, very important terminology. If you really understand that will understand how the massive MIMO or the active antenna in general improve the performance in the MIMO in general or in general beamforming, these kind of things, which we're going to discuss in details in next sessions. So actually, as you can see here in the left figure here, this is just showing three figures. The first one is very small unit, which is called the dual polarization, which we just highlighted in the previous slide. This dual polarization, for example, I mentioned about plus 40, plus 45 minus 45, they call dual slant polarization. As you can see, this is actually two antenna element. As you can see, this antenna element, again, we highlighted in the very beginning. This is the basic building block of something called antenna array or antenna subarray, which is this one. We'll explain about it now. But this smallest unit of the antenna, it's just a single emitting unit, which is called dipole, for example, as a dipole. And this element, it can radiate or even receive electromagnetic wave individually. This one can transmit and receive, this one can transmit and receive individually. So The more antenna elements you have within the antenna, the more gain you will have, because you will have much higher gain and much more control over your antenna. How this can be done? For example, first of all, this can be combined into this part, and this it can be combined into one block, as you can see here. And this block will have several antenna elements, and this called antenna subarray. This antenna subarray is just a group of antenna elements as mentioned here. This then we can have multiple subarrays within the the antenna itself, which is at the end called antenna array. And this is actually at the end, this is how the antenna looks like. If you remember in the very beginning, we show one figure showing how the massive MIMO looks like. If you look here, I just brought this figure here again. As you can see, this is exactly the same. As you can see here, this is the smallest unit, which is called antenna element, and it can having this is very small, small element inside antenna element can now have this kind of the final figure of the massive MIMO antenna, which is consisting of all a small or composed of multiple sub arrays of that, or multiple antenna elements. I will explain what exactly means by antenna sub array when we discuss now about this figure. So this is how the antenna looks like. And again, the higher the antenna elements you have, the much better beam efficiency, beam gain, and even antenna gain itself can increase, and these kind of things. Just keep this into your mind after now. So, for example, after the subarray being like combined into this and making two subarrays, as you can see here, the first one is here, and the second subarray is here. Now we have two subarray, which is building this kind of antenna array. So what kind of gain is expected if you have more subarrays within the antenna array? First of all, if you zoom in here, this will be explained with exact subarray and the second subarray here. So first of all, you have two vertical dimension now. So this is can give you this kind of 2D dimension. Usually in the passive antenna, it was just one component, or we didn't use to have this kind of different vertical planes. It was only one vertical plane. For example, here you have 8 horizontal. For example, you have 4 in the horizontal or row, 4 rows here, or 4 horizontal, multiplied by 2, so it's 8. And you have two vertical plane. This is the first vertical one, and this is the second one. And the vertical plane in general here is consisting of 4 antenna elements. For example, this we called it as vertical plane, the first subarray, having 4 antenna element inside, and each antenna element having two dipoles. So as you can see here, so this is actually the idea of having this kind of separation of two subarrays within the antenna. This is can give you some control over your vertical plane, so you can, for example, make a tuning to try to improve the high rise building. So this actually example is giving example about 16 TRX, which is 16 transmission receiver. And this is again how you can know that. If you have this kind of figure, you can look into if you found that the antenna is being divided into two dimensional like this, or two subarray. This means you have the first vertical and second vertical, so you have two vertical. And the horizontal in general, you can calculate it through counting this kind of row and multiply it by two which is dipole. So it will have, for example, 1 2 3 4, it will be 8 horizontal. And if you multiply these two horizontal by vertical, you will have 16 TRX, which is antenna transmitter and receiver. And to calculate the number of antenna element in general here, it's like have different ways. The very easy way is just to multiply 4 multiplied by 8, then you multiply by 2, so it will give you 64 antenna elements. Or there is another way to calculate it, but this kind of complicated. For example, it mentioned here how many vertical elements you have per TRX. Vertical elements. So vertical, you are speaking about this one. For example, here there is four antenna elements are combined to form one transmission in the vertical plane. That's why you mentioned that we have two vertical plane, because the first one is here, the second one is here. So we have 4 antenna elements. So this one will be 4 antenna elements. Then how many vertical TRX transmission you have? You have the first one with this one, and this is the second. So we multiply by 2. And how many horizontal in the TRX? So we counted in the horizontal, we have only one here, only one to generate the transmission. So to generate the horizontal plane. And how many T transmission? So we counted that you have 4 transmission, which is 1 2 3 4. That's why it's 4T for the horizontal TRX. Then you multiply it again by the two dipoles, which is you have the dual polarization. You have two, so and then this will result into 64 antenna elements, which is composed of that. So just to give you a quick explanation, in this kind of example, this is give you again, whenever you have dividing this into two subarrays, it give you again in terms of the vertical plane. in the vertical plane, because now you can have more adjustment in the 2D dimension. You can make adjustment for the vertical plane, not only the horizontal plane. But what if you increase the, instead of having like, for example, removing that and keep it only one clock for all of it? So the more antenna elements for the one transmission, the higher the gain, for example, in the horizontal plane or even the vertical plane. We'll explain this in the future, like with more examples, just to be clear. But for example, assuming that in the vertical plane you are using 4 QRX or 4 antenna elements, this means you will have, okay, I control over your vertical plane, but if you increase the number of antenna elements, instead of 4 you make it 6 or 8, this means your beamforming or even that antenna directivity in the vertical plane will be even much higher. Same for the horizontal. If you have more in the horizontal, this will be even much higher. So expect now, for example, if you have 64T or 64R, it will be even much higher in the horizontal and the vertical. So you can have even much more gain or beam forming and also antenna gain as well, and all the other stuff which you mentioned in the very beginning. This will go through it in the future as well. One important point to mention, that this is just something very known, that usually between the antenna elements or the antennas in general, you will have this kind of wavelength, half the wavelengths between them, and this is just based on many studies being done before. This is will improve your diversity, because the antennas will have distance between both of them, so they can experience different distances. So this can give some space diversity gain as well. So this is actually one also very important point, and we'll explain about it more in details actually in the verse. So in summary, the antenna terminology, you have the smallest antenna element. Can be composed into something called antenna subarray, and you have the antenna general or the antenna array. This can be composed even for multiple small antenna elements, or can have different subarrays in general. And if you remember, you'll hear all the time this kind of called array gain. Array gain means that you have many sub-elements, antenna elements within the array. So this can give you a higher antenna or higher antenna array gain, which is one of the gain of the massive MIMO or MIMO in general. We're going to explain next slides. This is just one quick example for the 88R antenna. For example, you have here in the horizontal at 4 multiplied by 2, it will be 8 horizontal, and you have only one vertical. So, for example, you don't have two, you have only one vertical here, and the vertical again is consisting of 4 antenna elements. So this is how it looks like. Even it will have this kind of ports. Each one of those will have one antenna connector, as you can see here. And again, you can multiply 4 by 4 by 2, it will give you at the end 32 antenna elements. So this is for the active antenna, for example, 88R. Passive antenna, sorry. Let's move forward. Okay, now in this slide, I believe you might be familiar about, which is really very, very important to understand it, because again, this kind of gains, whatever we have here, it's even become much better or much, much better in the massive MIMO. So this gain was already there in the MIMO, and it's already the same even introduced in massive MIMO, but much better efficiency. So let's explain one by one. If you remember, in general, multiple input, multiple outputs, which is a multiple antennas system, which is having this kind of MIMO, it's usually used to have a different types, right? Which is called SIMO, which is single input, as you can see here, from the transmitter, and multiple out, which means that you have single transmission and multiple receiver at the transmission. For example, in the transmission and the receiver. And the mobile side, which is being received in the downlink, you have 4 antennas as an example. So it can receive and from 4 different antennas. And this is usually called receive diversity, because the receiver side we use to have a multiple antennas. The second one, which is about the MISO, which is a multiple input, single output. So again, this is the opposite way around. You have multiple transmission, you have multiple antenna transmitting the data, and only one receiver. So you will have only a single output, which is single antenna received, and this is you will call transmit diversity. I'll go in very deep dive about the meaning of both of them and how the gain being observed, because this is very important to understand. And last one, which is a combination for both of them, which is multiple input, multiple out MIMO, and this can be 4T4R, can be 2T2R, and so on. And this is giving additional gain, can have both receive diversity and transmit diversity, or spatial multiplexing. And again, this is again just in very high level. I will go through details for all of them, because it's very important to understand. For example, the multiple antenna gain here, can have first of all, which is being mentioned by the MIMO, the spatial multiplexing, which is very known that you are transferring 2 different stream of data. For example, data 1 here and data 2 here, to the antenna to the receiver, and but the receiver must be supported as well to receiver to be able to receive from two different directions. It's usually happening in a very good radio condition, and this is can double your throughput. For example, instead of getting one data stream, you get two, so it can double your throughput. And usually we have different types. In next session, I will go through how those works for open loop and again closed loop MIMO in general. Then we have the diversity gain, which is can receive diversity and transmit diversity. I will explain both of them now in details. And now we have the array gain and beamforming. And within the beamforming array gain, as we just mentioned in the previous, the more the antenna elements, it's kind of beamforming effect, which is increasing your directivity towards the user. So you can, for example, as this particular example, is the more that the antenna elements within the antenna, can improve the array gain. And all of that already available in the game, in the MIMO, traditional MIMO, and it's become much better in the massive MIMO. Then you have the beamforming in general, and beamforming improve the efficiency of the single user MIMO and multi-user MIMO. Just to highlight, all this kind of single user MIMO, multi-user MIMO beamforming is not something new. It's available. It's exists since the traditional MIMO, which is starting especially from 44R and 88R. But it was used to have a very minimal gain or limited gain because of the number of the limited antenna. So let me explain in details each of those because it's very important about the receive diversity, transmit diversity, and the beamforming and the gain general. So the first part I would like to start here, it's about the receive diversity. First of all, these kind of inputs, it's trying to improve, as you know that we have this channel theory, which is, if you remember, this is it's called C, called the bandwidth, okay, multiplied by log 2, then 1 plus CNR or signal to noise ratio, which is C refers to the channel capacity in bits per second or maximum data rate in general. Then you have the B, which is bandwidth in hertz available for data transmission. Then you have the receive signal or the interference channel and noise power across the bandwidth in general. So, in general, to improve the throughput or the capacity, you need to improve, for example, the bandwidth, increase the bandwidth, or improve the signal to noise ratio. And actually, the diversity in general being here in this part, trying to improve the quality through adding additional antennas, even in the receiver or even in the transmit. And also, this M can be in the during the multiple stream transmission. This is you can, for example, multiply this by 2. So in general, this is formula. In the beginning, it was without M. But when you introduce a MIMO, now MIMO is playing a factor in improving even the CNR, doubling the capacity whenever, doubling the throughput whenever you have a spatial multiplexer. So let's move through one by one quickly to see what we can understand about the SIMO, MISO, and the other two are things with array and beamforming. Before jumping into the details about the SIMO and the MISO and other array and beamforming, because MIMO is combined both of them. Usually, as you can see, whenever you see any figure in any explanation, you'll find that usually this is the diversity gain. You'll find that there is two transmission being sent from the transmitter, like two signals being received. Maybe it can be the same signal, and for example, two receiver being received. So if these two signals or data, which is D1 and D1, which is mean the same data being transmitted twice, it's uncorrelated, so you can get the combination of both of them to get a better performance here. This was a high-level understanding of the diversity gain, and the array gain is using more antenna elements to try to generate a beamforming effect through making a higher directivity towards the user. So this can be improve the coverage and the quality as well. And spatial multiplexing, this is the easiest one, which is you have two streams of data being sent to the user with different data being sent. And the multi-user MIMO, where you have two different beams being sent. Each user can get the full resource blocks. So the resource will not be divided by both of them. No, each one will be shared different resource blocks. For example, layer 1 will be address user 1, layer 2 will be address user 2, and each one will get the full resource blocks. This was the high-level explanation. Now let's go through the SIMO to explain in details how the receive diversity is being achieved if you have only one single transmission, and even what is the difference between the receive diversity and transmit diversity. Okay, this is the first part about the SIMO, which is single input, multiple output. So you have a single transmitter from the antenna side, from the input B or GNB side, transmitting from single antenna, and you have a multiple receiver from the U side. So you have only one data being transmitted in the propagation channel, which we explained before. This can, during the propagation, they can like suffer from scattered data, from multipath, and so on. So how the receiver or whenever you have four receiver can achieve the receive diversity, and how this kind of receive diversity can be achieved, especially if you have a single transmission from the NUB side. Okay, in general, the receive diversity can or may be implemented via two different combining methods. The first one, it's called selection combining. Okay, selection combining, where the combiner at the U side selects the branch with high CNR among the M receiver or among the receiver. For example, you have a four receivers, so he will receive this signal from his four receivers. So he will select the one which is having the high quality. For example, they select the best antenna of the four, which are having the best or the strongest CNR. Means you will use only one antenna at a time. So it will just evaluate which one have received the signals in a better quality, so it will use whatever being sent. So the first one called selection combining. And this is not usually the one that's being used. Usually the one that's being used, which is more effective, it's called maximum ratio combining, MRC. What it means by maximum ratio combining, the receiver will try with the receiver can be, by the way, from the unit B side or from the UE side. For example, if the UE is transmitted uplink and you have four antennas here and this one transmitted from one antenna, it can also have similar impact. So, but here we're explaining the downlink direction where you have one transmitter and four receiver. So again, the second method of the receive diversity, it's called maximum ratio combining, which is MRC. What this one do actually? It actually weights, as you can see here, for example, you have the transmitter here. So it weights, you have, this is X, the transmitter, only one transmitter, and you have the receiver, for example, tell you YM or whatever, if you have more antennas. So Y1, Y2, and so on. So it will weight this signal, it will make a weight for this, it will weight each received signal based on its quality. So for example, the stronger one among all of these kind of receiver antenna will get more weight, and the weaker signal will get less weight compared to the others. Then it will combine all the weighted signal into one. So this is meaning that the UE or the receiver in general will combine the observation from all these antennas, which is four antenna, and instead of using only one of them, which is the strongest one, it will take all the observation into consideration and it will combine all the observation into one, and this will make the detection into this combined observation. It will make only one combined observation, which at the end will make the combination of all the observation here, and it will give you a much signal. As for example, this example on the right here, you have signal received from antenna 1, signal received from antenna 2. It will combine both of them. For example, at this particular situation, signal 1 was being attenuated. Here it was much better, so it will get a better bit again as a combining at the end. And same for the other spikes up and down here. And this is how it looks like. And like for simple analogy, you can think it like listening. You are listening to someone in a noisy room. And if you use your both ears means multiple receiver, and you focus more in the ear that hear better. You focus more on one ear which is hearing better. For example, in one room, maybe you have one ear hearing much better than the other, and you can just trying to give more attention to this ear, giving more weight to this stronger or the one which is hearing better, which is the stronger signal. You will understand the speaker more clearly than using just one ear or treating both of them equally. For example, if both of them, one is weak and one is stronger, and you're just trying to listen with the strongest one only, this is might be less compared to if you're trying to give more weight to the strongest ear while trying to also utilize the other one to get more information. And remember, we mentioned one very important point that in the very beginning, we mentioned that usually in the antennas, usually transmitter receiver, we should have some kind of space antenna, like the differences between which was half the wavelengths between the antennas, and this is called space antenna. It should be sufficiently far apart from each other, so each one of them can experience independent fading in each branch, which is again was being mentioned as half the wavelengths, which is being based on many studies. This was the appropriate value. So this is actually how the SIMOs being worked. So again, to summarize, it can be even through something called selection combining, where the receiver select only one branch of those which having the best quality, or combining all of them through as this figure, for example, to try to get the maximum gain from all of them. So it can hear only even you have one transmitted signal, it can hear it from the four receivers. So it will combine all of them, then it will give you the gain. So this was about the SIMO. Now let's jump into the MICE part to explain what is the main differences. But one thing to highlight in the receiver, he understands very well what is the propagation channel for each of those, because the receiver or the UE, he can measure the DMRS, for example, or can measure the CSRS, cell specific reference signal, and he can modulate each of those antennas. So the propagation channel is very well known to the UE. This is one very important information, because this will cover the difference in the next slide about how it means. So now let's move to the next part about the MISO. And by the way, I will add this all slides in the details in the video description after the video. And before moving to the next one, I just would like to highlight. Now assume you have only 4 receivers, okay, in the UE side and even in Unit B side or Unit side. Assume now what will happen in case of massive MIMO. For example, in the Unit B side, you have now 64 receivers. So the gain will be even maximized for larger receive antenna. This is so this can having a reflection in your uplink receive signal or uplink performance, right? Because you will have much more antennas in the unit B side. Still, the UE having limitation, so the uplink direction can have even much better improvement. As I remember, it can even go to very high values, maybe 8 dB. This is, as I remember, I need to refine and recall this information, but in general, it would be even much better in the massive MIMO. So that's why I'm trying to explain this kind of details to be able to understand from where the gain is coming whenever we increase the number of antennas, which is called massive MIMO. Now let's move forward. Okay, now it's about the multiple input single output, and this is actually very challenging, and you need to really understand it. Here you have a transmit diversity, which means you have multiple transmission and only one receiver from the E side, for example, or the opposite way around. But usually this is from the U side. So there is one very important point I mentioned in the last one, in the very end of the SIMO, that uh, that you should understand that there is something called channel knowledge. What it means by channel knowledge? For example, when you mentioned about the receiver is knowing about the propagation channel or the knowledge of the channel, whether it's having very poor, what is the condition of the channel, through reading the pilot channels. Pilot channels can be DMRS, can be cell specific reference channel. So it's understand very well about the channel knowledge or about the propagation channel in general, but not the opposite way around. For example, the transmitter is being sending from he don't have any knowledge about the propagation channel. So he will do the transmission from different direction or whatever, but he don't have knowledge unless he requested for that and receive the feedback, which is usually called receiving feedback about the radio condition, for example, this kind of BMI, CQI, rank, and so on. So, but in the normal case scenario, he don't have any knowledge. So whenever he transmit, he's blind. He don't know what's happening in the propagation channel. So in this case, how, assuming there is no feedback or without feedback, like we can assume the both cases. So in this case, how the transmit diversity can achieve the gain? First of all, the received diversity gain is usually much better than the transmit diversity gain. But let me explain to you how the gain can be achieved using the MISO or the multiple input single output. Okay. Actually, there are basically two different ways of achieving the gain, okay, of the transmitting diversity. First one is asking for the channel knowledge, which is through the feedback. It will ask the U to give the feedback about the channel knowledge. So once the U feedback the channel knowledge through BMI, for example, it will give him the knowledge about the channel. It will tell him this is my CQI, this is my BMI, this is my rank. So the transmitter will understand fully about the current channel condition here, and you will know all the information about the user. So in this case, you can utilize this kind of multiple antennas, okay, to make this kind of transmit diversity or the array gain. That it will utilize all the antenna elements or the antenna to try to make more directive beam towards the user, which is called usually array gain through like focusing the signal toward this particular receiver. And this is usually called maximum ratio transmission. The last one was calling maximum ratio receiver. This one called maximum ratio transmission. So this is the first part. If it's received a channel feedback, it will generate this kind of antenna gain, antenna array gain, which is mean you will have more directive signal towards the user to improve the quality and signal. Now, speaking about that, assuming that the unit B or the unit B doesn't have any knowledge or having a very partial knowledge about the channel, it doesn't know what is happening in the channel, so it cannot make this kind of beamforming or, in other words, which is more accurate, the array gain, directing towards the user in a static beam or whatever, just trying to make a more directive signal. It cannot do that if it doesn't have the feedback. So in this case, what will happen? Actually, in this case, it will use another technique, which is called space-time coding. Space-time coding. This will be used. Why? What means by space-time coding? Actually, this is a easy one. This is means space-time coding. This means it will provide from this four antennas. It will send or provide the gain through sending redundant information across different antennas. Okay, but again, how it will make sure it will be received? Okay, here. First of all, it will make redundant information. It means data one will be sent, that the same data will be sent through the forward transmission. But again, we have called it space-time coding with space-time diversity or whatever the name. Space means that the transmitter, he know that between each of those antennas, it's having a different space or different distance. As we mentioned again, wavelengths, half the wavelengths. So it knows that the propagation or the channel for that it will follow a different propagation wave, or the wave will follow a different direction. So this is the first part. So it knows that each one of those will have a different propagation way through moving through the propagation channel. Okay. The second one, it will transmit it in different time, and this is like or different time slots, for example. So this is will ensure, for example, that the one of these data will be coming in faster, received in faster way to the receiver, or of even improving the receiver from the side. So the antenna will receive the data four times, and it will just select the best one of those at the end, because it received four versions, so it will receive getting the most of them. And you can think again, like let's try to simplify it. Think like this, like you are in a classroom. For example, assume you are a student or teacher or whatever, but both of them will start speaking in different, will use different strategy. For example, this space time. What it means, for example, first of all, that but not at the same time. It will be in sequence, which is again the time diversity, and also they get use of the space diversity. For example, the first speaker will be in the very beginning, or the standing in different position. For example, one is in the beginning of the class, but at the end of class. So the blockage will be different between both of them. So now think about it. Now this is called space time. So you're speaking in different time and from different direction. So this is like you receive the signal twice. So you will again make sure that one of them for sure will be better than the other. So this is actually at the end will give the gain from the transfer diversity. But again, the receive diversity usually give better gain because the UE is very aware about the channel propagation all the time. So this is actually make it more easy for the receiver to achieve the gain. And this is actually the key differences that from the SIMO, which is the receiver, multiple output. The receiver is knowing about the channel feedback, so it can having much better performance. And the transmit diversity doesn't have any knowledge about the receiver. This is the main differences, and this is how the transmit diversity and receive diversity gain being achieved session, because it will be about the beamforming gain as introduction for whatever we get for massive MIMO, and even the array gain to explain to understand what is the main difference between both. Okay, now here this is will be just going through the beamforming gain. Again, beamforming is not a new concept. Like if you think that beamforming is a new concept which is introduced in massive MIMO only, this is not a very accurate information. Okay, actually, beamforming in general is it has been introduced to the mobile communication system in general since the beginning. For example, especially if you don't have this isotropic now. Okay, so for example, that the normal sectorization, if you have three different sectors, this is called the beamforming. You have sector one here covering this area, sector two covering this area, sector three covering the above area, for example here. So the sectorization itself is one shape of the beamforming. Yes, it's static, yes, it's fixed, but it's one shape of the beamforming. The as mentioned here also, that whenever you make down tilt, up tilt, mechanical or electric, or you're making RF shaping, general changing the azimuth, this is also sort of beamforming as well. Yes, both can be considered as passive beamforming or static beamforming because it's again in a fixed location. But this kind of beamforming, because at again beamforming, you're trying to move the beam even down, up, or to right, to the left. So this can be even done by the tilt or RF shaping. So this is the first point you need to understand. This is exist from the very beginning, okay? Especially when you start using this kind of sectorization and so on. And and here I'm mentioning an example about the passive antenna where you have 88R, you have 8 horizontal and 1 vertical, and this is like kind of 1D beamforming. The second one, which is 1D beamforming, where you can have a kind of automatic redirection of the beams. Like you can have a beams kind of beam steering. You can direct some beams towards a specific users, and this usually in 4G TM7 or TM8. And this is only was being done in horizontal plane, which is horizontal plane used called 1D beamforming. As you can see here, for example, this is in horizontal plane. You can direct different beams to different users, and this is for sure the gain of that was very limited because you used to have less number of antenna elements inside here. And again, you can see now, if you remember the very explanation, that all the antenna elements is only considering within the antenna. We don't have this kind of subarrays, different subarrays. So we don't have any vertical plane. So we cannot change the vertical plane. So just quick introduction before getting to the details for massive MIMO next slides. So this will be actually the differences compared to the massive MIMO. For example, just like slide differences, we'll have more details about it. But for example, in Massive MIMO, first of all, introduce 2D beamforming. 2D beam means one, if you have high-rise building, you can have this kind of elevation, or they call it a vertical azimuth, vertical plane, so it can even direct the beams to the higher buildings. And the horizontal beams even is here, and is even getting more sharper because if you compare this, for example, here, compared to this, both 88R and 64R, you'll find, for example, in the horizontal plane, used to have two elements. Now you have an antenna element. You have one, two, three, four, five until eight, and even in the vertical plane same. But even in the vertical plane now, it's being divided into, for example, here this mentioned a four vertical. This is the first one, subarray, second subarray, third subarray, fourth subarray, and this is giving advantage through giving again through the vertical plane actually. So this is how the vertical plane is being happening. But if this 64 are having only one vertical, this means you don't have a control over the elevation or the vertical plane. It will be only horizontal if you didn't divide it like this. And all that will be controlled by will be explained details how you can optimize that, how the vendors will give examples from 3GPP PP that how vendors or how in general this being controlled by the massive MIMO. And this is just was a quick, not very quick to be honest, but it was like a summary about the gains. And again, whatever gains you have now in the massive MIMO, it was already being covered by the traditional MIMO, but it will be even much better or much higher now because of this kind of more antenna elements, which is giving more control, more sharper beams, more control, more directivity for the beam forming, and you will have even horizontal and vertical plane, which is called azimuth plane or called azimuth or elevation plane. So this is called 2D beam forming, and all more details will be covered next slide. But the last part I would like to cover here, I will go through the details also for that part. This was kind of the evolution of MIMO and beamforming in general. And in 4G, you used to have two or four or eight antenna, and this is usually used to have a different transmission mode. For example, TM1, TM2, TM3, TM4, TM7, TM8. TM7, TM8, for example, beamforming and multi-user MIMO, and you have the TM3 and TM4, for example, for open loop and closed MIMO. And this is used to have beamforming capability, actually from 44R as well, not 88R, but it was not that effective. 88R is more effective compared to 44R because I used to work, have a beamforming in TDD network where we used to have 44R as well, but the beamforming was really very, very low. It was almost negligible, especially if you compare to 44R. And the beamforming in general was only controlling the traffic channel, which is the PDCH. And during this, old legacy from T to 88R, we used to have also multi-user particularly in the 8 and even in the 4, but it was really, really very low, almost nothing. It was not almost not working. And there is a new concept introduced in 5G called beam management. We explain this like particular subject, have a different session about that, which was not being supported here. Then, before even going to the Massive MIMO, or Massive MIMO was even introduced first for the 4G TDD. I've been working in different networks for that particular stuff, and we did a lot of optimization. So it was very close to whatever we have in 4G MIMO, but with much better performance. For example, here it was working with the same transmission modes as the transmission mode here. Beamforming capability, now this was supporting the 2D beamforming or 3D, where you have this kind of elevation azimuth plane, which is vertical and horizontal, as you explained. You can even direct, but this was only for the traffic channels. You didn't have it for common channels, for example, as compared to 5G. And this was supporting even multi-user MIMO, and the bearing efficiency or the multi-user efficiency was much better or way forward, way better compared to the multi-user MIMO in the legacy or the traditional MIMO. and beam management was not being supported here. The last part here, it was again starting from 16T up to 64 and even higher. It was called 5G Massive MIMO. But in Massive MIMO, we don't have this kind of concept of different transition mode. No, all the channels now adapt the beamforming. And this is again supporting the same, having 3D or 2D, bringing high performance in beamforming in general. And the main difference is very, very important. We'll also go through this in much details with logs and main things. This supporting all the channels. For example, BDCH, PDCH, synchronization signals, and all the APU-CH, all these are being supported, and you have even bearings even much better. And now the beam management is being introduced. So just a quick explanation here. So next actually video, I will, before going to the Massive MIMO, I will cover just a quick recap about the 4G transmission modes and so on, open loop and closed loop, and even the antenna boards, which is just to facilitate or waive the understanding of antenna boards mapping and antenna mapping in general. And that's it for today's video. I hope if you like the video to just press like and share it and to spread the knowledge. Thank you very much and see you in the next video.